Hello, my name's Fantasia Whaley, and I'm going to be talking about the importance of allotropes. An allotrope is the different forms that an element can exist in the same physical state. The different bonding in the structures give rise to different properties. For example, did you know that diamond and graphite are both forms of the element carbon? This means that carbon atoms bond differently to each other, so in one case they form a very hard crystal, and in the other they form a writing utensil. In this video, we are going to focus on 4 different allotropes of carbon. First, we'll look at diamond. This gem has a tetrahedral geometry, meaning that each carbon atom bonds to 4 other carbon atoms. The structure is held together by covalent bonds, which is a bond that shares electrons between 2 nonmetals. Due to its strong and stable structure, diamond has a very high melting point and is very hard. However, it's also brittle and a poor conductor. Next we have graphite, which is a layered structure. In one layer, each carbon is bonded to 3 other carbons, resulting in a trigonal-planar structure. Within the layer, the atoms are bonded covalently. Each layer is held together with what is known as dispersion forces. Dispersion forces are a weak attraction between atoms that are caused by the placement of electrons. Electrons in 2 different atoms occupy certain positions that cause slight charges on certain sides of the atom, causing an attraction between opposite charges. Graphite also has delocalized electrons over each layer, which is when electrons are able to move freely over a large area due to a double bond that can be in different positions. Due to the different bond factors in the structure, graphite has a very high melting point, is a good electrical conductor, and can resist temperatures of up to 3,000 degrees Celsius. Now we'll move on to graphene, which is actually very similar to graphite. Graphene is in fact just a single layer of graphite, so we already know that the structure of the bonds is trigonal-planar and that there are both covalent bonds and delocalized electrons in the structure. This causes it to have a very high melting point and to be a good electrical conductor just like graphite. However, since it is only a single layer with covalent bonds, graphene is immensely strong. It is 200 times stronger than steel, and if a sheet of plastic wrap were made of graphene, it would take the force of a large car to break it. Last is fullerene. Its molecular structure is a spherical cage of alternating 5- and 6-membered rings. It also has a trigonal-planar structure so that each carbon only bonds to 3 other carbons. Each sphere is held together by covalent bonds, and multiple spheres are held together by dispersion forces. It also has delocalized electrons over the entire sphere. All of these aspects cause fullerene to have a lower melting point than graphite, graphene, or diamond, to be a poor electrical conductor, and to have poor solubility. The reason this is also important is because the allotropes of carbon have very different applications. Diamond is used for cutting, drilling, and grinding. Graphite is used as an electrical conductor and is used in thermochemistry. Graphene is used in electronics and is still being researched about its use for strength. Fullerene is used in technology, that being mostly electronics and nanotechnology. Allotropes increase the usefulness of a single element. Understanding them and how their properties differ allow us to find other applications of a single element.